How does an artificial intelligence system move from a starting point to a solution? Search algorithms make that possible by exploring states, testing actions, and working toward a goal. You will see the main search methods, how path quality is judged, and how these ideas are applied in practice. Search algorithms are fundamental to artificial intelligence because they help systems find solutions by exploring a defined state space. They are commonly grouped into uninformed search and informed search. Understanding these methods is essential for solving complex problems effectively. A search problem includes a state space, an initial state, a goal state, and a set of actions or transitions. The initial state is the starting point, and the goal state is the desired outcome. A cost function can also evaluate each move, such as time or distance. Uninformed search explores the state space without extra knowledge about the goal. It depends on the problem structure rather than on guidance from a heuristic. Common examples include breadth-first search, depth-first search, uniform cost search, and iterative deepening search. In problems where all costs are equal, it is guaranteed to find the shortest path. Breadth-first search explores all nodes at the current depth before moving deeper. Its main limitation is memory use, especially when the search tree becomes wide. Depth-first search goes as deep as possible along each branch before backtracking. This can make it useful for deep searches, and it requires less memory than some alternatives. However, it may not find the shortest path, and it can get stuck in loops. Uniform cost search expands the node with the lowest cost first. That makes it suitable for weighted graphs where move costs vary. Instead of focusing only on depth, it focuses on the accumulated path cost while searching for a solution. Iterative deepening search combines useful features of depth-first search and breadth-first search by increasing the depth limit step by step. It is memory efficient and complete, though repeated searches increase computation time. Search can also be optimized by avoiding redundancy and preventing revisits to explored nodes. Informed search uses heuristics to guide the process toward the goal more efficiently. A heuristic estimates the cost from a given state to the goal. By adding this extra knowledge, informed methods can reduce the amount of search needed. Greedy best-first search selects nodes using only a heuristic estimate of closeness to the goal. This can make it fast, especially in simple problems or small search spaces. But speed comes with a trade-off, because it may fail to find the optimal solution. A star combines the cost to reach a node with the estimated cost from that node to the goal. This balance helps it search efficiently while still aiming for path quality. When the heuristic is admissible and does not overestimate, a star guarantees an optimal solution, 0405. An optimal path is the best possible path according to a defined criterion such as lowest cost or shortest distance. A satisfactory path meets the problem requirements without being the best or the shortest. Satisfactory paths often favor quick results, while optimal paths place more emphasis on accuracy. Dynamic programming solves problems by breaking them into overlapping subproblems and storing results to avoid repeated work. It is used in shortest path problems as well as resource allocation, scheduling, and robotics. Bellman equations provide a mathematical framework for optimization, including shortest path methods. Heuristic search methods can improve computational speed by narrowing the search space. Their effectiveness comes from directing attention toward promising choices instead of exploring everything equally. This makes them valuable in problem solving, especially when fast decisions matter. An effective heuristic should be admissible, meaning it never overestimates the cost to the goal. It should also be consistent, which supports steady progress through the search. Examples include Manhattan distance for grid-based pathfinding and Euclidean distance for physical spaces. Heuristic methods often improve speed because they reduce the amount of search required. The risk is that a poor or biased heuristic can reduce accuracy or lead to suboptimal solutions. Choosing a search strategy therefore means balancing efficiency with the quality of the final answer. 02, 03, 04, 05. Search algorithms are used in pathfinding, puzzle solving, and game playing. Pathfinding appears in navigation for games, robotics, and maps. Puzzle examples include mazes, Sudoku, and the 8-puzzle problem, while game decision-making can use methods such as minimax and alpha-beta pruning. A star supports safe, efficient path planning around obstacles in real-time navigation. In robotics, search algorithms support path planning by helping a system navigate obstacles and find efficient routes. A star and related methods are used for shortest path planning in dynamic environments. One example given is autonomous vehicles planning routes in real time while considering safety constraints. Minimax can work with heuristic evaluation functions to select strong moves in games such as chess and Go. An example noted is AlphaGo, which used advanced heuristics for strategic gameplay decisions. A practical search project starts by defining the problem through its state space, initial state, goal state, and actions. Next comes choosing an algorithm such as breadth-first search, a star, or depth-first search based on the requirements. After implementation, testing, debugging, and optimization refine correctness, memory use, and execution time. A simple program can solve a maze by representing it as a grid where open paths and walls define possible movement. Breadth-first search is used to find the shortest path in an unweighted maze, and the sample program reconstructs the path from start to goal. The same approach can be extended with a star or dynamic obstacles. Search algorithms help artificial intelligence define problems, explore choices, and reach goals. You have seen the main algorithm types, the difference between satisfactory and optimal paths, the role of heuristics, and practical uses from robotics to maze solving. The key is choosing and refining the method that fits the problem.